Hey guys, this is Vinay from KLU, currently studying third year CSE. This presentation is about fuzzy and crisp relations and their operations. In this, we'll be discussing about the definition of fuzzy and crisp, their differences, their relations, representation of the relations, and the operations done in fuzzy and crisp. A crisp relation represents presence or absence of association, interaction, or intercommunication connection between elements of greater than or equal to two sets. Whereas fuzzy, it generalizes them, which classifies them and gives them memberships or grades according to that. Let's say, for example, in fuzzy, we are having XYZ, we want to categorize them based on their honesty. So it will be like extremely honesty, partially honesty, very honest, not so honest, extremely dishonest. Based on the activities or based on the lies or based on those factors, we'll be saying whether their X is extremely honest or Mr. Y is extremely honest, Mr. Z is not so honest, so on. See, and whereas in crisp, the answers are always like 0, 1, true or false, yes or no. It's like binary values. Binary values. Let's say we want to check whether an item is fluid or not, or liquid or not. Water, it's a liquid, whereas wood, it's not. Book, it's not, and so on. Crisp relation, it's a collection of order bits. Let's take two sets, and the representation is as follows. Let's take two set non-empty sets. This is the representation. A product B, where A comma B will be the resultant, which means the result value. And A belongs to A, B belongs to B. And for n sets, it's just write A to A1 to and AN and the product, and A1 to AN all the subsets to be given in singular set. And A1 to A1 belongs to A2 belongs to A2, A up so on, AN belongs to AN. This is the representation. Next, there are total four methods of representation for relations: bipartite, coordinate matrix, and digraph. In bipartite, if there is a relation to A to B, it is going to be joining or matched to that. If not, it will be left like that. As you can see, A1 is related to B2, A2 is related to B2, A3 is also related to B2. So it both are joined like this, and A4 is only related to B3. That's it. And whereas in coordinate, we will be taking one axis as a, one axis and Y, and if there's a relation, we'll be plotting them, and we'll be joining all the points, and the resultant graph is the diagram. Next, for matrix, let's say for crisp, it is either 1 or 0. If it's satisfying, if these values of A and B are satisfying the relation, then it is 1. If those doesn't, then it's a 0. So we can, based on this, we can say that A and B, A1 and B1 are satisfying, so it's a 1. A2 and B1 are not. A3 and B1 are not. A4 and B1 are not. In digraph, it is whether if it is directed to itself, which means if it's a relation to itself, it is directed to 1, and if it is directed to 2, it needs to also have relation. We can represent this digraph in a matrices form. If they are directed to any of the other values, then it is 1. If not, it is 0. Based on that, the first row will be like 1 1 1 0. As 1 is not directed towards 4, it's a 0. And for 1 1 0 1, it's for 2, as 2 is not directed towards 3. The size of the graphs are like these directed graphs matrix is like 4 into 4 if there are 4 values, 3 into 3 if there are 3, and so on. And we can plot accordingly. In this way, we can convert digraph into matrix. Next, let's take an example here, C and D, where C has 1 2 3 as values and D has 4 5 6. Here the given relation is that D equal to C plus 2. First, we have to find a product of C and D, which is 1 comma 4, 2 comma 4, 3 comma 4, so on up to 1 comma 6, 2 comma 6, 3 comma 6. We'll be checking all the values that are all the values, and the resultant relation we'll be getting as 2 comma 4, 3 comma 5. This is the sagittarial representation or pictorial representation. Since 2 plus 2 is equal to 4, or 4 equal to 2 plus 2 as given in the condition, 4 is equal to 2 plus 2, or 5 equal to 3 plus 2. So it is joining, and in matrix representation will be given 1 if there is a relation, if not it is a 0. So it's a 0 0 0 1 0 0 0 1 0. Next, operations. There is the null relation, which is all the values will be 0 of any size of any graph of size n, any matrix of size n. Whereas in a complete relation, all the values are 1 in the matrix of size n. In the union, this is the representation for this. This is for union, this is for intersection, this is for complement, this is for difference. The representation in A union B will be finding the max of XA and XB, whereas an intersection will be finding the min of XA and XB, whereas a complement will be subtracting it from the whole. Here, let's take A 1 0 0 1, B equal to 0 1 1 0. First, let's write what are the result values of 0 union 0 is 1, no 0, sorry, 0 union 0 is 0. For the rest, 0 union 1, 0 union 1 union 0, 1 union 1. For all this, it's 1. Whereas for 0 intersection 0, 1 intersection 0, 0 intersection 0, 1, the value is 0. For only 1 intersection 1, the value is 1. So now we can find the resultant. A union B, 1 union 0, it's 1. So 1 union 0 is 1. Here 0 union 1, 0 union 1 is 1, 1 union 0 is 0. And the resultant matrix of A intersection B is going to be like 0 0 0 0 0. And for the A complement, it is 0 1 1 0. Just happen to be equal to B. Next, composition and max min composition. In composition, let's take X, Y, Z. These are 3. And then the relation between X and Y is R. The relation between Y and Z is S. And ROS is composition relation, which is X comma Z, which gives the overall relation between X and Z based on these two relations of R and S. Where max min will be finding max of the min values in the fuzzy relation. As earlier said, we will be having answers like not so true, may be true, may not be, partially true, like that. So the values are in the range 0 to 1 always. And it is the representation of that two sets where A has X comma Y as the variables, where X belongs to A, Y belongs to B. For example, here you can see, as earlier we have talked about, as earlier it is said about A and C. It is a digraph. A and C are connected, so the weight of that direction is given. C and D, weight of the direction is given, and so on. We'll be placing the weights of the value if they are joining in this. And the sum for this, the relations if there is a sum, we'll be finding max. If there is a product, we'll be finding max to min. If there is a scalar, we'll be finding another. Here for this, we are taking A plus B. We'll be finding A and A. In this, we'll be checking parallel columns and rows. 0 0.2, 0 point, which is max. 1.0, so 1.0, 0 0.5, 0 0.1, 0 0.5, 0 0.0, 0 0.0, both are same, so 0 0.0 itself, 0 0.4, 0 0.0, 0 0.4, 0 1.0, and so 1.0 will be getting 0 0.1, 0 0.0, 1.0, 0 0.1, and so on. Same way for this, we'll be following the rules in the above, as said. In the operations, there are two: inverse, complement, intersection, and union. And these are the representations of finding the relations. Let's take, for example, a relation is the set of R, and this is a matrix set, matrix S. We are finding matrix set R union S. 0 0.3, 0 0.30, 0. In the above we have some a plus b, no, same way. 0.2 max values of these we'll be finding and placing them here. For intersection, for complement, we'll be subtracting 1 minus 0.3. Here for some, we'll be subtracting it from the whole, which is 1. Next, composition of fuzzy relation. Here we'll be finding max of the mean. And coming to the difference between fuzzy set and crisp set, fuzzy set, it's the always it's gonna be like may not be in there, but whereas in crisp the always answer is always certain. It's either yes or a no. The partial values can be involved in fuzzy set, but in crisp there's no possibility, so it's only one or true or false or 1 0 or 1. Applications is that we use fuzzy in controllers, and we'll use crisp set in digital designs. Fuzzy sets have infinite set of values, or is only 2. By value means only 2. Thank you.